Okay guys, so in the previous classes we ended up to the Jacobian matrix, and I developed the MATLAB code, and now it's time that we derive equation of motion, equations of motion of a robot. That's right, we have to derive it. Why? Because we're going to use that to control the robot. Until this point we were talking about the kinematics. Jacobian that I was teaching you was like this: velocity of n effector and the omega of n effector, remember, was Jacobian. That was 6 by n is the number of the joints, degree of freedom in joints angular velocity. That's right. So this way you go. This is forward kinematics. You are providing the joints angles, and finally you calculate this. So this is forward kinematics. But the backward is that you are giving this the position of the end effector angular velocities. At the end you get this, the joint angles, and this is the case that we are doing in the control of the robot, this case, which is inverse kinematics. In the control of the robot we are doing inverse kinematics. We are giving the trajectory, like as you saw in the back in my lab, we are giving the trajectory of the end effector. Now we're going to find the joint angle that generates such a trajectory, right? So, and remember that the Ji was like this, for refreshing your mind, was Zi minus 1 cross product of O of end effector with respect to the base coordinate system minus OI minus 1 and Zi minus 1 if the joint was the revolute, and the Ji was Zi minus 1 if, and 0 if it was prismatic. That's right. This is what we have done in for a 3D degree of freedom in the 3D dimension. And if remember that the Zi minus 1 was rotation matrix of I minus 1 and in k direction. Right? We have done this in theory and in MATLAB. But this relation, this Jacobian relation, this cannot be used by itself for driving dynamics of a robot. This cannot be used. So what's the solution? May you have seen, may not. I'm teaching you from scratch. The solution is our Euler Lagrangian formula that in the literature we know as Lagrangian formula. So what is that? I'm writing here. This is that how you derive for 2 degree of freedom, for 3 degree of freedom, for 10 degree of freedom, for 50 degree of freedom robot if you have. You are using this formula, okay, to drive the dynamics of the robot. Is tau k. Time derivative, this is time derivative. Rho partial derivative of L, that is for Lagrangian, over angular velocity of the links, generalized coordinate variables. again Lagrangian function, what do we name it, or the angle of the joint simply, and this is the torque, or this is the, as in the control we name it as U, control input. That's right. This semester I'm teaching the linear system theory, and I'm teaching to students how to design the state feedback to drive any system, including robots. So, and this is the control input that you have to design. You have to design. You're gonna tell me how. The simplest is that you passed with me or other professor at SDSU. Was that undergraduate control? Yes, PID controller. So the simplest version is that you design a PID controller. If I have time, I'm gonna do that by MATLAB code, okay? To drive your robot. But first, before that, you have to drive the dynamics of a robot that you are working on. So first, so this is the Lagrangian formulation. In Lagrangian function is sum of, we say sum, say n from k from number of the joints to n, tk. This is what? Come on, you know from the dynamics course. This is kinetic energy. Energy that is generated based on the velocity of an object. Means that any moving object has kinetic energy. Minus sum of k from 1 to n joints. Suppose that you have n joints. Obviously, its corresponding links. So, and this is pk. This is what? Potential energy. Potential energy of the links. Understand? So this is the Lagrangian function. So before going to the examples, let me teach you by a simple example how this Lagrangian equation we derive. Its original equation. How can I say that this relation is a valid relation? Simply speaking. Look at here, guys. Okay. Look at here. You have a mass, a particle mass. You are applying, this is U, F, external force by your hand. Suppose this is your hand. It looks like the cooking ware, but suppose this is your hand. So your hand apply a force there, that's right? Okay, this is your hand. So you want to move it up, so it accelerates, that's right? So it's gonna be m, mass of that, y double dot. Suppose here is y direction. So, but we know that the gravity, our beautiful gravity, gonna resist that. So mg. This is dynamics, that's right? We know we name it as the free body diagram. Remember, free body diagram that we were showing in the ME202. No, ME220. Free body diagram in ME220 at SDSU. That's right, dynamics course, free body diagram. This is the trivial step that you when you drive the dynamics equation. And now we get help from our lovely Mr. Newton. Some of the forces in y direction is the mass in the acceleration on that direction. Or we were seeing that m-a-y acceleration in y direction. That's right. So what are the forces here? If here is positive, here is going to be negative this side. So this is positive, this is positive, this is negative. Going to be F, the forces. This is the force, and this is gravity force. Minus mg is equal to my double dot. Or if you move to this side, you get my double dot plus mg is equal to F, and this is the dynamic of when you try to move an object from ground. Okay, now let us take a deep look to term by term of this, our simple and trivial example. First this. Look at here, guys. My double dot. My double dot from the high school or kindergarten level mathematics is d over dt of y dot. That's right. Because this is velocity. Time derivative of velocity gonna be acceleration. I can write this, right? So this is equal to, again. This is equal to, because m is constant, mass of the object, so it goes inside. Do you care? No. So d over dt my dot. I can do that. This is trivial algebra. Now you can write this as this. Look at here, guys. D over dt, d over dy dot over differentiation variable is the velocity now, and 1 over 2 my dot square. Am I right? Yes, because when you taking the derivative respect to y dot, it comes to this finally. This is trivial algebra. If you don't know, go to Google on tickets. So, right? So now tell me from dynamic course, what is this? What is this 1 over 2 mv square? What it is? Kinetic energy. So we say it's K or T, because I said T, that's right. Let me see, I said T. Sometimes they say K, so it doesn't matter. T, kinetic energy. That's right. So on the other hand, let me summarize this finally. On the other hand, my double dot is d over dt of what? Round t respect to round t respect to round y dot. Now guys, look at this. Have you seen this? Almost d over dt. This is L still, but bear with me. Over round k q dot, because this is for the joint. That's right. It's close to that. Good. Now let us look at. Let me change the color. This term, mg. When you see mg in dynamics, means that you have potential. That's right, potential force, potential energy. Let us take a look at that. Mg is equal to, you can write like this, d over dy mg y. Yes or no? Respect are going to be mg. What is this? Yes, it is p. So at the end of the day, it's going to dp over dy. Oh, good. It's familiar? Almost, yes. Here we go. Your y is q, joint angle. Almost, not exactly the same. Understand? So now, if I define, as I did previously, look at here, I said L is T minus P. So Lagrangian, as I said, is K minus P or T here. T minus P, kinetic energy. So kinetic energy here is 1 over 2 my dot square. We just derive together. Look at here. Here we go. And the potential is mgy minus mgy. Now let me now examine the Lagrangian equation. What is that? I'm writing here again. Look at here, guys. This is not magic. So I said Lagrangian is this: d over dt round the Lagrangian function over round here gonna be y dot instead of q minus round L over round y, gonna be force tau. Here is force F. Right? Here is tau, because in the robotics you are rotating the joint, so you need torque. In robotics, this is torque. torque. That's right, torque, Newton meter. But here when you're lifting up an object, you need just force, Newton. That's right, unit is Newton, right? Now let us examine that. That's right. So round L over round y dot, round L over round y dot, what is that? I'm just doing here, round L over round y dot, gonna be m y dot. Look at here, only is 2 y dot. Round L over round y, do you have seen here y? No. Do you see? Yes, gonna be minus mg. This is trivial algebra. Now I'm putting this inside the Lagrangian equation to see that it works. So with d over dt time derivative of round m y dot minus mg is equal to f. So you see that this is what? M is constant. Time derivative of y dot is y double dot plus mg is f. So you see that the Lagrangian equation gives you the same result that you got from here from the Newton's second law. So you can use Lagrangian for robotic systems. Understand? Now, let me go to the simplest robotic problem that you can have. Here we go. Using the Lagrangian equation. Suppose you have a robotic arm. We have seen a million times in my classes. And that's this one link robot. Suppose one link robot. This mass center is here. Mass center. The length of the robot is L and it's rotating as theta, and then you're gonna design a controller at the end, hopefully. So this is tau, that's right, or U, control input. Now I'm asking, using the Lagrangian equation, derive the equation of the motion. So first of all, you have one link. So your L is T minus U because you have your one link. So we know that from dynamics that the kinetic energy for a solid object, not the particle, so it is for this link gonna be 1 over 2 m v of mass center square respect to the base coordinate system. Here's the base coordinate system, guys. Here we go. Okay, I'm saying MC, mass center is here. MC respect to the base coordinate system plus 1 over 2 and omega, okay, or square respect to base coordinate system, and I of mass center, okay, respect to base coordinate system. This accounts for the translational velocity. This accounts for rotational velocity. That's right. This is kinetic energy. Minus U. Guys, I'm just putting a larger version of that here. This is mg. Here is L over 2. And here is theta. And here is your base coordinate system. This is your datum. Here is x and y. So kinetic energy means this normal distance. That's right, this normal distance. How much is that by trigonometry? Yes, it is L over 2 sine theta. Yes or no? So it's gonna be, so this is gonna be mg. So your u, let me write here, gonna be mg L over 2 sine theta. But the question is, the kinetic energy has sign positive or negative? I want that you think answer. Obviously it is positive because this is above datum and has the potential to generate work. If you release the link from here, it goes down by itself. So it has the potential, so it is positive. So your U gonna be minus U, minus this, minus mg L over 2 sine theta. Right. Now I have to calculate this V. Right. I know that the omega is what? Theta dot, obviously. Understand? Why this stop? Oh, it's a typo here, guys. This is with respect to its own mass center, respect to I, link I, y equal to 0. So what is V? How we calculate that? The position vector of MC with respect to the coordinate system, reference coordinate system, gonna be what? This vector plus this vector. This vector is L over 2 cosine theta in I direction minus L over 2 sine theta in plus L over 2 sine this. So the velocity of MC, mass center, with respect to the base coordinate system, gonna be minus theta dot L over 2 sine theta I plus theta dot L over 2 cosine theta j. So we need this square, so it's absolute value. So absolute value of the VMC gonna be this L over 2 over 4. We can factor out theta dot 2, factor out sine square plus cosine square. For God's sake, this is 1, and the result is what? L over 2 theta dot, but it's the power of 2, so the L is 1 over 2 m in L2 over 4 theta dot square plus 1 over 2 theta dot angular velocity in I respect to sorry guys, I'm getting older. This is 0 with respect to IMC. The mass this is the mass moment of inertia with respect to the center of the link. Gonna be 1 over 12. You can find it even from the Google for a link. ML square minus mg L over 2 sine theta. So this is the Lagrangian for this simple one link robot, right? So now we have to use our famous so we have to say round L over round theta dot, and we have to calculate round L over round theta as a part of the Lagrangian equation. Here we go. As a part of, because your Q is theta here. Okay. So round L over round theta dot, you have 1 here. 2 with 2 goes to hell. ML square over 4 theta dot. So ML square over 4 theta dot. 1 is here. And another is here, theta dot. 2 with 2 goes to ML square plus ML square over 12 theta dot. That's right. Do we have theta dot here? No. So we are done with that part. Round L with respect to round theta. Do we have theta here? No. Here no. But here we have. Gonna be minus mg L over 2 cosine theta minus mg over 2 cosine theta. So if you do that, this is gonna be 12 is 3 plus 1 in m. I'm doing for you that you understand. It's gonna be 4 over 12. It's gonna be it's gonna be 1 over 2, 1 over 3 ml square theta. Now again we have to use the Lagrangian and put it here. So you're gonna have d over dt time derivative of 1 over 3 ml square theta dot minus round over round q dot. We have done that already. Hold on guys. We have it here. Minus mg L over 2 cosine theta is equal to tau. Obviously this is 1 over 3 ml square theta double dot plus mg L over 2 cosine theta is equal to tau. Right? Now you can validate this by our dynamic course. Use the moment equation. You get the same result. I bet $1 million. I bet that you will get the same result for this robotic link. Listen. Now the question is if I have n degree of freedom robot, how I have to develop that. As I said, this is the Lagrangian equation. Round L over round Q dot K minus round L over round QK is tau K. But if you have this kind of robotic system, look at here guys, 1 2 3 4 5, see you have 5 degree of freedom robot. This theta 1, theta 2, theta 3, theta 4, I don't know, theta 5. Suppose you have 5 degree of freedom system, or like as the Baxter robot I have in my lab, I have 7 degree of freedom robot. How we can use Lagrangian equation to do that? So what you're gonna do, you're gonna say L, let me change the color because it's too much orange. L is again from K1 to N TK minus K1 to N PK, that's right. Then you can expand like this. Use K1 to N because you have the solid links has both component of their mass centers. Okay, they have the linear velocity and the angular velocities, that's right. So it's going to be 1 over 2 mi, mass of the link I, velocity of the mass center of I respect to the base coordinate system, which is here always, square, plus 1 over 2 omega of I, the joint of that link respect to the base coordinate system, square, in I mass center, okay, and an I mass center of that, minus sum of now PKs, K from 1 to N, if you have only solid links, no elastic links, is MIG, its mass center respect to this. So for here, so this is this, for this is it this, respect to the base coordinate system. Understand? Huh? Okay. Hold on. Okay. Now, having this, now let me go and suppose I have a 2 degree of freedom planar robotic system. Here we go. I'm gonna derive this to show you how much it's difficult if you derive the equation of motion of robotic system by Lagrangian and your hand. This is very difficult when you extend into the high degree of freedom robotic system. So this is L1, L2, you have theta 1 and theta 2. So this is O. This is 2 degree of freedom robotic system and the planar. So what you're gonna do, your Lagrangian has these two components. K from 1 to 2, TK, because you have two links, 2 degree of freedom. And K from 1 to 2 to PK. Okay. Mass center of 1 is here, mass center of 1 is here. So T1, because you have two T's, is 1 over 2. Suppose M1 VC1 square plus 1 over 2 I1, because the both on the planar, their axis of rotation is out of the plane. That's right. Right hand rule. So this is IZZ. That's right. IZZ from dynamics. Mass moment of inertia in the Z direction. Axis of rotation in the Z direction. In theta dot 1 square. And the T2 gonna be 1 over 2 M2 VC2 square plus 1 over 2 IZZ of, this is 1, this is link 2, theta dot 2 square. When I say theta, let me say omega. I have intention. Omega 1 and omega 2. Respect to base coordinates. Please take attention to this problem. If you understand this, you understand the rest of the robotics, how to derive dynamic equation of the motion and write its MATLAB code. If you don't, you won't understand the rest. Okay, so we see one. As I did previously, we have the R1 mass center of this and the mass center of this. R1 is, as we wrote here, L1 over 2, half of that, cosine theta 1 in I plus L1 over 2 sine theta 1 in J. Yes or no? This is the position of mass 1 with respect to base coordinate system. Now for mass 2, R2, because we want to calculate this and this first, gonna be, okay, its X is, guys look at here, this is X naught, as I taught you previously, base coordinate system, Y naught. So we calculated this first, look at here. And now for mass 2, you have to calculate this value. That's right. So this value is this value in X plus this value. That's right. So this value is L1 cosine theta 1, this value, plus this value. How much is that? How much is that? It's very clear. Look at here, guys. How much is angle? How much is angle? This is theta 1. Yes or no? This is trigonometry. So this value is plus L over 2 divided by 2, half of that, in cosine what? Theta 1 plus theta 2. Right? This is a simple trigonometry. So the mass center of the link 2 with respect to the frame coordinate system is this. Now plus, now I'm talking about this. This is that. Let me change the color. This is, come on. This is this plus this, right? Again, this is obviously from this gonna be L1 sine theta 1, and this is again plus L over 2 sine theta 1 plus theta 2 in J, right? Huh? So now, but we need the VC and VC2. So from here you get VC1, VC2 gonna be minus, I can factor out L1 over 2 theta dot minus sine theta 1 I plus cosine theta 1 in J. This is the vector of velocity of link 1 for 2 degree of freedom robot. VC2, good luck. You get minus L1 theta dot 1 sine theta 1 minus L2 over 2 theta dot 1 plus theta dot 2 because time derivative in sine theta dot 1 plus theta dot 2. This is only used for I plus L1 theta dot 1 cosine theta 1 plus L2 over 2 theta dot 1 plus theta dot 2 cosine theta 1 plus theta 2 in J. So simply you get that VC1 square gonna be like as the previous case L1 square, this is 1 theta dot 1 square divided by 4. Do it at home. VC2 square gonna be this square plus this square. So this square gonna be L1 theta dot 1 square. I'm just doing in my brain, okay? Plus L2 over, this is L2 over 4 theta dot 1 plus theta dot 2 square. And look at here, this minus minus when it goes to square is positive, so it's gonna be, look at here, I'm writing a different color, it's gonna be plus 2 of time in this and this, gonna be L1 L2 theta dot 1 plus theta dot 2. Now sine theta 1 why I write theta dot here? They don't have that. Sine theta 1 and theta 2. Now this time plus cosine, I'm again taking this out, cosine theta 1 plus theta 2. But we know from trigonometry that cosine, say A minus B from trigonometry is cosine A cosine B plus sine A sine B. So you see, we have the same here. So the result of this, comparing that, gonna be cosine of theta 2. All right. So now let's go. I want to just show how cumbersome it is even for a 2D freedom robot, and we have to look for classical method to use Jacobian I taught you into symbol, into classical derivation of equation of motion. Okay, so again, now we have Vc1 square was L1 square theta dot 1 square divided by 4. Vc2 square was this L1 square theta dot 1 square plus L2 square over 4 theta dot 1 plus theta dot 2 square plus this L1 L2 theta dot 1 plus theta dot 2 in cosine theta 2. This is only V's, guys, only V's. Hold on, it's warming up. Okay, understand? Now we calculated those. Bingo, we calculated this, calculated this. Now we have to come to this and come to this. If you remember, when I was teaching the robotic, I had a formula, and I said that remember this formula I taught you, that say omega n respect to 0, remember, was let me bring up and write exactly like that because it's very clear. Yeah, remember this, I taught you omega 1 respect to 0 plus r1 respect to 0, remember the rotation matrix, omega 2 respect to 1, r2 respect to 0, omega 3 respect to 2, and finally rn minus 1 0 omega n respect to n minus 1. Remember that I taught you exactly? So now here you have to use this formula exactly for this problem. So omega 1 respect to 0. So your n is 1. Omega 1 respect to 0 again is omega 1 respect to 0. This part, right? Obviously, this is very obvious. How much is that? This link, theta dot 1. Theta dot 1 in k direction, obviously. That's right. So we have this. Now omega 2 respect to 0, we know the answer, but for validity of whatever I have taught, it is r1 respect to 0, omega 2 respect to 1. So r1 respect to 0 is this again, 0 0 theta dot 1 plus, remember, r1 respect to 0.
I can learn to
r1 respect to 0, as I taught you, remember. Let me do it here for you, refreshing your mind. Here we go. Suppose that side, this is when we're setting up the coordinate system. Here was x2, right, y2, and the z2 is out of the side. So, and here is x1, sorry, oh, sorry guys. Here we plot like that. Okay, so here is, look at here guys, this is your reference coordinate system as we were doing. X0, Y0, and Z0 is out of the page. Here is X1, Y1, that's right, and Z0 is out of, Z1 is out of the page, and here is say X2 and the Y2, that's right. So R1 respect to 0 is obvious, right? Or system 1 respect to 0 means if you transfer it here, remember here is x1 y1 0. I'm just writing here plus r1 respect to 0, x1 directional cosine, remember, gonna be cosine theta 1 sine theta 1, and there's z. Here gonna be you're gonna be minus sine theta 1, right? It's projection on this. Cosine theta 1 and 0, and the z's, they are parallel. In omega 2 respect to 1. We have it here, guys. Omega of link 2 respect to 1. How much is that? Theta dot 2. Right, let me do this here that you can see it visibly. See, omega link 2 is rotating with respect to link 1 as theta 2. So it is theta dot 2. In which direction? Obviously in z direction again. So no doubt that this result to this 0, 0, theta dot 2. Do it at home. You will get the same result. So omega of link 2 with respect to the base coordinate system is theta dot 1, as I taught you previously, theta dot 2. Now we have it. Understand? So this term for this 2 degree of freedom gonna be like this. So your T1, let me write here, next page. So T1 gonna be 1 over 2 M1 L1 square for theta dot 1 square plus 1 over 2 I1 ZZ, okay, in theta dot 1 square. And no doubt that if you can find in any published book or a Google that I is 1 over 12 M1 L1 square respect to the mass center theta dot 1 square. So T1 gonna be finally, let me change the color, gonna be 1 over 8 M1 L1 square theta dot 1 square plus 1 over 24 M1 L1 square theta dot 1 square. See, 24 4 M1 L1 square theta dot 1 square. So the kinetic energy of the first link, for God's sake, gonna be 1 over 6 M1 L1 square theta dot 1 square, as we expected. So T2 gonna be, look at here, guys, this term, big term, gonna be 1 over 2 M2 L1 square theta dot 1 square. There's no dot here. L1 plus L2 square over 4 theta dot 2 square plus L1 L2 theta dot 1 plus theta dot 2 cosine theta 2. Oh, this is the first term of that. Plus, get here, guys, 1 over 2 again plus 1 over 2 1 over 12 IZ M2 L2 square, okay, in omega. Omega of that is what? Is this theta dot 1 in multiplied by theta dot 1 plus theta dot 2 square. Right, let me see if I'm wrong. Oh, we have here this let me see this so it's gonna be theta dot 1 plus dot 2 square. So huge term, right? And now P1 obviously gonna be M1 G L1 over 2 sine theta 1, and the P2, no doubt from trigonometry you have to calculate this again, is this M2G L over 2, it's gonna be this your P2. M2G L1 sine theta 1 plus L2 over 2 sine theta 1 plus theta 2. Bingo! These are only, so now L1 gonna be T1 minus P1, L2 gonna be T2 minus P2. You have to implement this putting here, and now you have to calculate one by one of this, and I want that you do it at home. It's gonna be round theta dot 1 minus round L round theta 1 gives you the first control torque, and you do the same for the second link. You see that it's very cumbersome, guys. It's gonna be very cumbersome, but I want that you do it as homework and drive the equation of motion of this. So now in my lab I have a 7-degree of freedom robotic manipulator. You have to have L1, L2, L3, L4, L5, F6, X7. I have a rescue robot 18 degree of freedom. Good luck if you want to do by hand. So we have to go and find the classical method to use the Jacobian I taught you and drive the equation of motion of the robot. Teach you the next class.